Okay, class, let's start today's lesson and we'll continue discussion in chapter 7, the Laplace transform. So we have already introduced the definition of Laplace transform. Okay. And it has two-sided and one-sided, or bilateral and unilateral. A bilateral Laplace transform, okay, is defined as the integral from negative infinity to plus infinity, f of t and e to the power negative st dt. It's in fact an extension of the Fourier transform, since the Fourier transform, if we still remember, assume this S being a pure imaginary number j omega. And we use the Fourier transform in frequency analysis and so on. The single-sided Laplace transform is the most widely used. In fact, very few applications use the bilateral one. So we're going to focus on the single-sided or unilateral one. The reason being that for most of the cases, we only focus on functions that start with time 0 and goes to probably infinity. And 0 just artificially selected time points as the start of our observation. We can assume before this time point there's no input to the system at all. So the lower bound of the integral will be 0 instead of infinity. And the rest is the same as the bilateral Laplace transform, and this is what we already have. And similar to the Fourier transform, we also have the inverse Laplace transform as well. And for the inverse, both the lateral and bilateral share the same definition. Okay, 2 pi j is in fact a relatively complicated way to do the inverse transform than the inverse Fourier transform. The reason being, we have to set up the paths of the integration for complex numbers and so on and so forth. And as a matter of fact, very few people do the inverse Laplace transform using the definitions. We usually use the tables and all the references to help us, or some calculation techniques to help us find the inverse Laplace transform or the time domain function. And last time we have, mentioned that there's one kind of interesting or important concept. If we again come back to the bilateral, bilateral Laplace transform, Fourier transform, we can see here and here the difference is one is a generic complex number S, the other is a pure imaginary number j omega. And in fact, S can be written as the real part sigma plus j omega, the imaginary part. And we introduce this sigma so that for any function f of t, okay, I'll write it here, e to the power negative st will be f of t e to the power negative sigma t times e negative j omega t. And if we somehow can assume here, okay, this is our function, then we're actually calculating the Fourier transform of this blue guy. And the sigma, if we select correctly, we can bound the entire signal within the lower bound, within the certain bound, so it doesn't blow up to infinity or doesn't remain constant. Remember, in Fourier transform, we come to certain scenarios that we have f of t, let's say if equal to 1, and it's difficult to find the Fourier transform directly if we don't use other techniques. So, and we can look at some examples as well. For instance, remember that we have been focusing on unit step function a lot. So let's say the unit step function, if we want to do the Laplace transform, how easy it's going to be. Of course, it will be unilateral based on the definition. U of t will stay here. E to the power negative st will stay here. Okay. And since u function either take value 1 or 0, and since from 0 to infinity, unit step function takes only value 1, will be 1 times e to the power negative st. And clearly using our usual calculus knowledge, it's not difficult to find out, well, this is going to be e to the power negative st divided by s with the limit from 0 to infinity. Okay. And plug in infinity here, plug in 0 here. Since this s has a real part, and if we select a real part correctly, let's say in this case s as a positive real part, then this infinity bound will lead the entire thing go to 0, while the rest will just be as go to 0 will give us another number. So we'll see how it goes. Sorry, when t goes to 0. So it'll be I used to use a black pen to do this. So the limit of e to the power negative st, of course this is when t goes to infinity, minus e to the power 0, negative 0 times t, of course this is 1, as we all know it. And for the first one, as I said, if s is a positive real positive real part, this whole thing will go to 0. If sigma is positive, where sigma is the real part of s. Okay. So, to sum it up, this guy is going to be equal to what? You have negative 1 over s, you have negative 1 here, so altogether, we're going to have just 1 over s. And to be, rigorous, we usually want to specify, what we call the region of convergence. Is, we have to use a certain condition, and this is what we have been using there. That the real part of s must be positive so that this guy will have a limit. Okay. Otherwise, if the real part of s is a negative number, this term will simply go to infinity, and there's no way we can calculate the entire thing. Okay. So let's move on. Now from this, whole thing we have seen, well, if we want to find something of interest, the region of convergence is something we have to specifically want to do this Laplace transform more rigorously. And as the text will point out, to find this region of convergence is usually very simple. We simply want, whenever we have these to the power st in our integral term, we want it to be decaying as time goes on. But not necessarily we always have a simple relationship like this. Sometimes we can get a little more complicated, but not dramatic. For instance, instead of looking at the unit step function, we can look at the exponential function, right? And remember in our discussion, let's assume we select our initial point or time of observation at time 0. So before that, there's no input. Only after that we have this input. we're applying this switch u of t to this exponential function. And let's see what happens. And again, integral from 0 to infinity. And since we already applied the switch here, the function is relatively simple. This is using the definition. And we have two exponential terms. Let's combine these two directly. We have negative a with negative s. Altogether, we should have negative s plus a. Now, since we have another exponential function, and since the integral variable is just t itself, we can simply write following the same scenario, and we'll find out what this is actually going to be equal to. Negative s plus a, okay, and then e to the s plus at with t from 0 to infinity. Now, what can we see now is, for the 0 is easy to taken care of. It's still going to be negative 1, since it's lower. But for infinity, now you have s plus a. Let's assume a is a positive number. I'm sorry, it's a real number. So to make this e to the power negative s plus a times infinity being reasonable, the only thing you have to make sure is this guy, this complex number, should have a positive real part. Okay, positive real part. So that when you apply this negative sign in front of it, this whole thing will go to 0. In other words, we're simply implying that we want this guy, the real part of s plus a, to be positive. And as a result, this whole thing will be equal to, not surprisingly, s1 over s plus. Okay, 1 over s plus. And as we can usually always see that, in fact, if we only care about the unilateral, we don't even have to use the switch, the unit step function. We have something like this because the Laplace transform already implies that we start the calculation from time 0. Okay. Now again, to be rigorous, we want to imply that this is our the regional convergence, but in implications we usually omit this directly, which is usually is not essentially important. It's not essential. And since Laplace transform is kind of extended from Fourier transform, they share a lot of properties, important properties. For instance, one of them is the linear property. Linearity. In other words, if we have two functions, f1 of t and f2 of t, and we want to add the two together, like this, okay, then the Laplace transform of the summation is in fact equal to the summation of the Laplace transform of each individual. Now this property can be used in both ways. Sometimes we can decompose a big function into two small parts. And if we're able to find out the Laplace transform of each individual, then we're able to find the Laplace transform of this big guy. And sometimes we can do dx as well. And later on, we'll apply this to study the time response, the response of the linear time invariant system, and we use this property extensively. Okay, now let's move on a little bit. In Fourier transform, other important properties include time differentiation and time integration. look at the time differentiation for a while. I mean, Fourier transform is relatively simple. If we want to do a Fourier transform of the derivative of a certain function, what we do, remember we do just j omega times the Fourier transform of the original function f of t. This is what we have, Fourier transform. Now for Laplace transform, things get a little messier, and we'll give the results directly. The derivation is included in the textbook that you can read about. The reason it got a little messier is because the Laplace transform we use here the unilever, which ignores the entire time region from -infinity to 0. So you have to take that into account. And this may create a little trouble. Not usually if, remember from Fourier to Laplace, you replace j omega with s, so j omega should become s, right? And it should be followed by the Laplace transform of ft, which is good. But because the starting point of observation for Laplace transform is time 0, we have to take that into account by adding this additional term at the end of this equation. And this is pretty important. This is very important in our subsequent analysis. So I put it here, and later on we'll use it again over and over. Okay, so this is the time differentiation. It's typically quite important. Now, we can also do some other things. We can look at, typically some other the transform of some special functions. For instance, the delta function. If we still remember the delta function, if we do the Fourier transform of the delta function, it should be exactly equal to 1. Similarly, if we do the Laplace transform of the delta function, using the definition, it's not difficult to find out. This guy should be equal to 1 as well. Not surprising. Okay. Now, sometimes we want to do a time delay. We want to do a time delay. A time delay will be, instead of f of t, we have f of t minus t0. So we shift the function by amount of t0. If t0 is positive, we're delaying it. And how to calculate it? We say, well, this is going to be the Fourier transform of your original function multiplied by e to the power negative j omega t. Okay. Negative j omega t. Now for the Laplace transform, as we can see, since we just need to replace j omega with s, what's going to be? Laplace Fourier transform becomes Laplace transform. And j omega t will become st. Will become st. So if delta function is going to be 1, then delta function delayed by t0. And if we take the Laplace transform, it becomes 1 times e to the power s t0. Okay, here I should have t0 here, t0 here. So it's quite simple. It's quite simple. Now we'll look at something that's not that similar as what I've seen in the Fourier transform compared to Laplace transform. And this guy is going to be the cosine and sine function. So let's see. What's going to be a cosine function? Okay. Maybe let me use the one from textbook so it will be consistent. Cosine of bt. And again, we want to find the Fourier and the Laplace transform. Remember, in Fourier transform chapter, the way to calculate it is using the Euler formula. And we're going to use it again. So 2 t plus negative j times b times t. Okay? And remember e to the power negative at will have a Laplace transform of 1 over s plus a. Right? And a can be anything. It doesn't have to be a real number, it doesn't have to be a complex number, it doesn't have to be an imaginary number. And here, since you have e to the power something times t, we're going to do that. So 1 over 2, 1 half is 2 here. First guy, 1 over s plus a is j times b, so j times b plus 1 over s plus negative j times b, so negative j times b. And we can combine them. We're having actually a pair of complex conjugate s plus j times b, s minus j times b. So s plus b squared. Okay, and on top, okay, we're going to have s plus jb plus s minus jb. So j times b, j times b cancel each other, and 2 and 2 cancel. At the end, the numerator will have s right here. Okay. Now, do we still remember what happens to the Fourier transform? So here I should reverse that's right like this. Now, for Fourier transform, this is the Fourier transform cosine. Okay, if you remember, it's going to be split in half, move 1 to the left, move 1 to the right. So you have 2 delta functions. B here, another delta function. Okay, and you can see sometimes they can be quite different from one another, quite different from one. Now for the sine functions, it's very similar. And again, we use the Euler transform. Minus s minus j. Okay. And it's easy to find out that we'll be able to find this guy.